Welcome to the second lecture of the lecture series on the non-traditional abrasive machining methods, and after the introductory lecture we will start today on a discussion on ultrasonic machining. So, what is ultrasonic machining? In this method, the method of machining resorts to percussion or hammering of abrasives against the workpiece with a tool. So, we have a tool, it is not directly impacting the workpiece, but there are some abrasive particles put in between the workpiece and the tool. These abrasive particles are hard and they are they can retain their shape, that means they are rigid, and therefore, they can cause impact erosion of the workpiece material when working in this particular mode of percussion. So, hammering is done by a body which is known as the tool, and the tool material has to be sufficiently ductile, so that it itself does not undergo brittle fracture. However, we cannot avoid the removal of material from the tool parallelly with the workpiece. So, tool wear is of sufficient degree, and it should also be fatigue resistant, because in order to increase the material removal rate, we are increasing the hammering rate to ultrasonic frequencies. So, if that be so, there will be dynamic loading on the tool material. So, it should be fatigue resistant, and the rate of machining is proportional to this hammering, and therefore, the frequency is typically say 19 to 25 kilohertz. So, if you are in front of an ultrasonic machine and it is operating at such a frequency, if you are very sensitive, then you might be hearing a very very high frequency sound, but most people do not hear it because it is beyond the audible range. So, let us quickly see what are the support systems which will be allowing us to remove material by this means. First of all, abrasives have to be supplied. So, they are applied at the machining site by being carried in a water medium generally, and it is called a slurry. Say you put volume per volume, say 20 parts of abrasives in 100 parts of water, and let it be applied by a nozzle, that means by a jet at the machining site, so that all the time the machining site is receiving fresh abrasives, and the debris of machining, that means removed material, broken abrasives, all these things are removed by that jet of water only. Once abrasives are used, they should not be used again, because first of all, abrasives will in that case will be contaminated with debris coming out of machining, and second, due to such a high rate of hammering, many abrasive particles will also be undergoing fracture themselves. So, fractured abrasive particles will not be that efficient as the fresh abrasives. So, abrasive slurry has to be provided to the machine site, and generally they should not be recycled. The tool has to be pressed against the workpiece with a slight pressure, because if there is no pressure, there will be no machining, no matter how much frequency of vibration you are providing, because ultimately the tool the workpiece will recede away from the tool if they are not pressed together. However, if we apply a higher pressure, thinking that higher pressure will allow us to remove material faster, maybe that is true for some area of work, but it will not ultimately help us, because higher and higher loads pressing the workpiece and the tool together will ultimately lead to crushing of abrasives. And once again, if the abrasives are crushed to smaller sizes, they won't be as efficient as before. And of course, abrasives have to have a higher fracture strength than that of the workpiece. The tool has to have higher fracture strength, obviously, because a lot of high frequency vibrations are coming in, creating a lot of stresses. This is a pictorial view of the basic support systems which are required in case of ultrasonic machining. At the top we have a transducer. What does the transducer mean? The transducer means that it converts generally electrical energy to mechanical vibrational energy. What can be the way in which it can be done? With this we will discuss in more detail later on. It has to have either some piezoelectric crystal to give rise to piezoelectric effect. I mean the reverse of it. That means you are providing electrical energy, you are getting mechanical vibration. And it can also be done by magnetostriction, in which you are providing once again electrical energy, and due to a magnetostrictive substance changing its dimensions under that effect, it will provide vibration. So, once this vibration is set up, this vibration is conveyed by that geometrically you can see, we can define it as a tapered or an exponentially decaying diameter. This body is called a horn. It transmits this particular vibrational energy from the transducer right up to the tool. That slightly colored portion, very small item sticking at the end of the horn, is called the tool. It has a shape whose conjugate shape is going to be produced on the workpiece surface. So, the purpose of this horn, which has a definite shape, is to amplify the amplitude of vibration. The amplitude increases from the transducer end to the tool end of the horn. Why do we do that? Because high level of amplitude is generally not produced by the transducer, so that its workload is low, but it is amplified by the horn. It is concentrated by the horn. The horn is held at a particular position shown by those two triangular supports, at a position where the vibrational movement is 0, so that it is not damped out. In this case, we have shown a small amount of weight put on a common balance, by the help of which we are able to press the workpiece and the horn together. Say if I put say a 1 kg weight, how much is the load that I am applying on the between the workpiece and the horn, between the workpiece and the tool? 10 newtons, that is all. So, that way with these support systems, and of course, the abrasive slurry is provided as shown, so that fresh abrasives are always supplied at the machining site. So, this way we can easily make use of the abrasives to get removal of material in case of ultrasonic machining. This is a very simple setup, and we will discuss each aspect of the machine. For example, the horn, the system of applying loads between the workpiece and the workpiece and the tool, etc., etc. All these things will be treated in good detail. So, let us have a look at the ultrasonic machining zone, or the actual site of machining. We have demarcated the tool by a trapezium, by 2 trapeziums basically. That means the opposite of this shape is going to be produced on the workpiece. Here we have shown that the amplitude of vibration at this end is 10 to 50 microns. That means it may be 10, it may be 20, it may be 50, like that. So, this is the end of the horn, the tool end of the horn. From the nozzle, slurry is coming out, which means that in a water medium you are carrying abrasive particles. So, these abrasive particles are everywhere, and after use they are getting deposited somewhere, and the correct or recommended practice will be not to recycle them. These are some of the shapes that we have machined on glass, ordinary borosilicate glass, with the help of our ultrasonic machine. What does it show? It shows that glass is having a very polished surface, but the flat ends of these machined zones are showing that the roughness is not that good. I mean, roughness is not that low as ordinary glass surface, but still, just imagine if I give you a glass piece and if I ask you to develop such recesses, okay, such portions, I mean such machined features, geometrical features on this glass, would you be able to do it by any means? But here it is shown, it is done very easily, and each of these cavities were about 1 millimeter to 2 millimeters deep, and they were done in about 1 minute of machining, just 1 minute of machining. So, that means you can do it very efficiently, because you can produce any type of shape that you have in mind, and you can do it quite fast also, and you can do it on a material which is very difficult to machine by other means. So, now look at the details of the machining process. What sort of abrasives are we talking about? Abrasives can be boron carbide. Why boron carbide? This is because boron carbide is the third hardest material at this moment in the list, topped by diamond, then comes cubic boron nitride. You might say, then why don't I have diamond? Well, diamond powder can be costly, if it is not synthetic diamond, but natural diamond powder dust, it can be costly. So, what about cubic boron nitride? That is also very costly. Boron carbide is also costly, but not as costly as the first two. So, it is sort of best option which is used very frequently in machining applications. You can also have silicon carbide. Silicon carbide is not that costly, but its machining rate also will be less than, say, boron carbide. Aluminum oxide, it is not as good as the previous ones, but it is not that costly. Boron silicarbide is known to be one of the promising candidates in this regard. Diamond powder or diamond dust is used on diamond, ruby, etc. Here we are seeing two pictures which we have taken for boron carbide particles, roughly say 44 microns, and silicon carbide particles, roughly of the same size, slightly larger. So, what do they show? They show us, they look just like randomly shaped stone chips that we used very frequently in the making of concrete. Okay. They are not exactly spherical in shape, that is what I wanted to convey to you, but they are having a flaky structure. But you will be surprised to know that in the mathematical models, I mean in the analytical models that are applied in case of ultrasonic machining, in most of the cases you will find that they assume the abrasive particles to be spherical. Now, obviously, that's wrong. So, in that case what is generally done is that it is assumed that they have a lobed structure, and these lobes are mounted on top of a sphere. So, that makes it a good, not good, but a workable assumption or acceptable assumption of the shape of the abrasive particles. So, let us see, this is 20 microns. Can you see, this is 20 microns, which will give you a good idea of the size average size of these particles. So, this is the assumption. If the abrasive particle looks to be bounded by straight sides and it has a flaky or it has a structure which is of this type, it is assumed to be of this nature. Why so? Because this allows us to assume the shape to a degree of reality. That means it is not fully spherical, to a degree of reality for analysis. If you take this shape, you will spend most of your efforts in representing this shape. Instead of that, just assume this shape. That means there are some spherical lobes of smaller diameter on a larger sphere. This is what we will assume. So, now the scene will change a bit. That means, on the basic spherical abrasive particle, we are having the lobe, and that is what we have represented, and its diameter is represented by a constant multiplied by the square of the abrasive grid diameter. So, the basic sphere that we have, it still has a diameter of d, and the lobes that we have, they are proportional to the square of the diameter, and this constant of proportionality is mu. So, this way we can relate the lobe diameter to the actual abrasive grid diameter, and in this case we can establish a relation between d1 delta indentation and large d, which is the diameter of the indented circle. Okay. What is this particular relation? We can have a quick look. If you have a look at this piece of paper, suppose this is the sphere, I mean this is the lobe. Therefore, we can say this must be d by 2, and this must be delta, and therefore, this is also d by 2, and this must be large d by 2. So, in this case we can frame the equation to be, sorry, this is d1, okay, d1 by 2 whole square is equal to d by 2 whole square plus d1 by 2 minus delta whole square, Pythagoras theorem. Okay. Now, if this be so, let us quickly see what it gives us. d1 square by 4 equal to d square by 4 plus d1 square by 4 minus twice d1 delta by 2 plus delta square. Now, since delta is very small, delta square can be neglected and this goes out. This goes out with this, and therefore, we have d square by 4 equal to d1 delta, which means d is equal to 4 d1 delta, or to write it clearly here, d is equal to d square. D is equal to twice root over d1 delta. Okay, this is the relation that we get. This is the relation that we get in this case. Simple geometrical relation from Pythagoras theorem. Here, if we go back to the expression here, d is equal to twice d1 into delta. Please note that here there is a slight mistake. The 4 underneath d square and the 4 underneath, the 2 underneath d1, etc., and the 4 underneath this d1, they have been missed, or none of the denominators have been provided. But you already know this calculation, that from the calculations by hand that we have performed, and therefore, this is acceptable because we have already proved it. So, kindly note the corrections to be made here. When I provide you with the PowerPoint files, I will make the correction in this one, in that. Okay. So, please note this needs some correction, but this one is correct. So, we will make some assumptions before trying to find out the rate of material removal that will be occurring in this case. What are these assumptions? They are actually very simple. The abrasive grits are perfectly rigid and hard spheres with lobes as shown. If the work material is brittle, a hemispherical volume of material with diameter d is removed per impact. These things actually we have discussed. All abrasive grits are similar and all impacts are identical. The MRR in USM is proportional to the frequency of the number of abrasive grits making impact. These will follow, if you apply your common sense, I think you will definitely agree that yes, these are all acceptable. Now, let us see what is happening when the horn is vibrating. When the horn is vibrating, what happens is that, at the end of the horn there is the tool, which I have not drawn, I have just drawn one integral horn. End of the horn is therefore acting as the tool. So, first of all, we are pressing the horn on top of the abrasives with a constant force F. On this is impressed, that means imposed. On top of that, we have the vibration, which is going to cause a fluctuation in the load. So, in that case, what do we have? First of all, we have the horn executing simple harmonic motion due to the vibration. So, it goes down, goes up, goes down sinusoidally with time. Now, what is going to happen when it is first of all, why have we drawn the horn and the grit lobe with a gap in between? This means that abrasive particles actually are not of the same size. So, if you consider the average abrasive particle, it will definitely have a gap between the horn and itself, because those abrasive particles with maximum diameter, with larger diameter than the average, they are going to hold up the horn. The horn is going to rest on the larger diameter grits. So, the average grit is going to be slightly below that. So, there is a gap between horn and the horn end and the grit topmost point. So, when when the horn is vibrating, we find that delta W plus delta T is the total amount of movement of the horn after it contacts the grit lobe. After it contacts the grit, I have shown only the grit lobe, but basically it is contacting the grit. So, when the horn has contacted the grit, after that it is undergoing a downward movement of delta T plus delta W. Now, what is that? What is delta T and what is delta W? We are arguing this way that since the abrasive grit is rigid, it does not change its shape, it does not undergo any deformation, but the horn undergoes, the tool undergoes deformation and the workpiece undergoes deformation. so that ultimately this delta t plus delta w movement is being sustained as damage or indentation on the tool surface and on the workpiece surface. So, total horn movement after contact is equal to delta w, which is indentation on the workpiece, and delta t, which is indentation on the tool. So, that is acceptable. So, what we have written is, we have made with that assumption that is the movement of the horn being equal to the movement of the I mean the indentation on the workpiece and the indentation of the tool, then we are drawing up a similarity of the velocities of the vibrating element. What is that? We are arguing that just like 4 amplitudes are covered in a time period. So, the distance is 4 amplitudes and the time is the time period. So, the average speed is equal to total displacement divided by time. 4a, small a being the amplitude of vibration at the horn end, at the tool end of the horn. 4a by t is the average velocity from that consideration, and the average velocity of the horn during the what do you call it, the impact, the indenting period is total distance travelled during indenting period divided by the time taken for that, and the time we are calling as delta t. So, these two velocities we are equating, saying they are occurring due to the displacement of the horn only. Both of them have the same source, vibration of the horn. So, they must be equal. This is actually not very correct, because whenever some body is vibrating, it has the maximum velocity at the mean position with 0 velocities at the extremities. So, it is not fully correct, but let us go ahead with this assumption and see what it yields ultimately. So, we have drawn up a relation between relation for delta t just by arranging these terms. That is good. So, after that what we are saying is, I am afraid some terms cannot be seen on the side. I will definitely tell you what they actually mean, because you cannot see it fully, at least I cannot see it fully on the screen. So, F t, the static force, we are making an equality between impulses. Impulse, what is impulse? Impulse is force into time. Okay. Force into time. So, we are saying that the steady static load, which is remaining constant over cycles of vibration, that particular product, force into time, that will be equal to the same value for the instantaneous force multiplied by the time. Let us see what we mean by that. So, instantaneous forces are changing. This is one instantaneous force, this is another instantaneous force. So, essentially it means if I try to multiply the instantaneous force with the time, I will ultimately be getting the area under this particular curve. Now, what is this curve? This curve shows that as the abrasive is more and more indenting into the workpiece and the tool material due to impact being driven by the horn, by the hammering action of the horn, as it is getting more and more impacted, it increases the force between the workpiece and the horn goes on increasing. And when at the end of vibration, when the horn is receding, it is moving back, then the force comes down and ultimately it reaches 0. This side is actually much more steeper. So, the highest force which is experienced, that is called F max. So, we can say how much is F max? If you ask me, I will say I do not know, we have to find it out. So, we basically find out the area of this triangle as half the base into altitude, half the base. This is time axis. I am sorry, I have not written it here. This is time and this is force. So, on the time axis, the interaction of the horn with the abrasive is only for delta t time when it is in contact. The moment the horn reverses, contact is lost after elastic deformation is released. So, we can say the area under these curves, it is equal to delta t, half the base, half into delta t into F max. That is why we have written here half into delta t into F max. So, that is being equated to force into the time period, that is the steady force into the time period. We are saying these two values will be equal. If they be equal, then delta t can be replaced from its original relation, and it can be written out this way: F into time period is equal to half into F max into delta t plus delta w divided by 4a into what do you call it, into delta t. Okay. Sorry, that is not supposed to be delta t, that is supposed to be time period t. So, time period t is on both sides and it will cancel out. We still have a little more time to see that. Yes, F max ultimately comes out to be, after cancellation of all the terms, 8 into F into amplitude divided by delta t plus delta w. So, can we say whether we have a relation, I mean an expression for F max? No, still not. While F is known, amplitude is known, delta t and delta w have not been found out till now. We do not know their values. So, let us proceed with the analysis to find out what can be delta t and delta w. Once it is found, we can know F max. Once F max is found, we can find out ultimately the material removal rate that is occurring. Okay. So, I will stop here as the time is up for the second lecture. We will again continue with the third lecture, in which we will ultimately find out the expression of material removal rate. Thank you very much.